Hello and welcome to the screencast for Chem Activity 33, Alkanes, Cycloalkanes, and Alkyl Halides, subtitled What Makes a Molecule Organic? You might notice the word organic, and you might think about the title of your textbook for this class, which is General Organic and Biological Chemistry, and you would note that since we have moved to organic chemistry, we have now completed the general chemistry section of the course. So you could think of the course as being perhaps 3/5 completed, with 1/5 for organic and 1/5 for biochemistry. Or maybe you could think of it as half over with 1/4 for organic, 1/4 for biochem, something like that. Table 1 is showing you the first 10 what we call straight chain alkanes. As you can tell by the pseudo structure, they're not perfectly straight, but they are called the condensed structures. So what we're going to do in this activity is relate things that we've already learned, which are Lewis structures, to these other kinds of structures, which I'm calling condensed structures and stick structures. Some books will call these line bond structures because the bonds are lines, so they're line bond structures, or something along those lines. Haha, no pun intended. All right, so let's move right into the activity. Here's a complete Lewis structure for ethane. And critical thinking question number 1 says, draw a complete Lewis structure for propane. Feel free to refer to the model where you find the structure for propane. Pause the video and write your answer now. Okay, so did you get that? Propane looks like this. How do I figure that out? There's a CH3, a CH2, and a CH3. So that's how we condense that up. When I look at the stick structure, I can see that there is a carbon here, here, and here. So each end and each bend is a carbon atom. So there's 3 carbon atoms. The hydrogens are not shown in the stick structure. So this is my carbon with 3 hydrogens, the second carbon with 2 hydrogens, the third carbon with 3 hydrogens. And you can see how the condensed structure can be written then CH3, CH2, CH3. And the stick structure like this. So, using that as a model, go back to the table and fill in the remaining blanks in the stick structure column and the name of the alkyl group substituent column. Pause now. Great, so you can compare your answers to mine. One thing that you are going to have to do is to be able to memorize the information in this table. And the names of the first 4 alkanes they're based on ancient names, and so they're not systematic. But once you get to number 5, they're based on prefixes that we've learned earlier in the class. So pent for 5, hex for 6, hept for 7, oct for 8, non for 9, and dec for 10. So those prefixes you've already learned. These first 4 you then just have to memorize anew: methane, ethane, propane, butane. If you're British, you say methane and ethane instead of methane and ethane. And so if you make some mnemonic device for these 4 letters, you can come up with your own. One I've seen before is Mom eats peanut butter. Just a way to help you remember the names of those first 4 alkanes. And then you just change the ending to get these ones over here, the substituents. Good? Number 3. Circle each carbon atom in the stick structure of butane, shown at the right. Which atoms are not shown in stick structures, hydrogen or carbon? So we did this before. You're going to circle each carbon. You can see that there are 4 of them, and hydrogens are not shown. Number 4. How does the structure of an alkyl group substituent differ from the structure of the alkane with the same number of carbons? See Table 1. So take a look at Table 1. Try to write a sentence that describes how the substituent is different from the alkane. Pause now. All right, did you say something like this? When I look at ethane, CH3CH3, and I look at ethyl, which is a CH2CH3, has a little dash in front of it, that's indicating that it must be bonded to something else. We'll see that soon enough. What I wrote was the substituent has 1 fewer hydrogen atom. Okay? Number 5. How can the name of an alkyl group substituent be derived from the name of the corresponding alkane? And write your answer in a complete sentence. Pause now. Here's my sentence. I made it short. Replace the ane suffix with yl. Do you see how that works out? Every time we just take the ending, which was ane, we replace that with yl, and that changes the name of the alkane into the name of the alkyl group substituent. Moving on. Once organic molecules get large, it is convenient to draw them as stick structures. Imagine if you have 100 carbons. You don't want to draw complete Lewis structures for 100 carbons and, well over 100 hydrogens, well over 200 hydrogens. That would just take forever. So it becomes a lot more convenient to draw them as stick structures. And each end and each bend represents a carbon atom. Here are the most common, what we call cycloalkanes, where you could say the head and the tail of the alkane are connected. So we have cyclopropane, cyclobutane, cyclopentane, cyclohexane. If you have a molecular model kit, and when I have these in the classroom, we build some models, and you can see how those models that we build look like these pictures over here in the right-hand column, the ball and stick model. So number 6. By extension, draw condensed and stick structures for cycloheptane. So condensed and stick. So pause the video and draw those now. All right, here are my attempts at doing that. Cycloheptane would have 7 carbons. So you'll get better at drawing these after you've practiced. 6 is pretty easy because we might be used to drawing a hexagon. 7 is a little more challenging, but you can do it if you practice. And then to get the condensed structure, so I drew them in opposite order. There's the stick structure. To get the condensed structure, you have CH2s. Notice that it doesn't really matter if I put the H's to the left or the right of the carbon. So if you, for like this CH2 group, if you wrote your CH2 like this, that would be equally fine. Nothing wrong with that. What sometimes students will do is they'll draw it like this, and then they'll put the CH2s out to the side, like this. That's not correct, because you need to be showing that the bonds are holding the carbons together. The bonds are connecting the carbons together. So here I'm showing lines, but they're not between the carbons. So don't mix and match. Either show the stick structure or the condensed, but not try to mix them like this. And I didn't try to draw the whole Lewis structure of these, but if you tried to draw the whole Lewis structure, then each time you had a CH2, you would have to put the CH2s out like this. So I'll just do cyclopropane. Oops. Right, so there's cyclopropane. with a complete Lewis structure. Much easier to just draw this. All right, branched alkanes. Alkanes are branched when the carbons are not connected in a continuous manner. For example, if you cannot trace all the carbons with your pencil or finger or your stylus, right, then from one carbon to the next, without lifting your pencil or retracing a portion, there's a branch. This is what makes it different than what we called in Model 1 the straight chain. The straight chain would better be described as unbranched. So this alkane, I can't trace the entire thing without backtracking, so it's branched. Number 7. A circle has been drawn around the longest continuous carbon chain in the first molecule. So the longest that I can do without backtracking. Do the same thing for the other 7 molecules. All right, so pause the video and do this now. Pause now. All right, so I've made an attempt at that myself. I will tell you that I've done one of them incorrectly. So one of them is wrong. So why don't you pause the video right now and see if you can figure out which one is wrong. Pause now. Do you see it? Let's look through them. This one is perfectly fine. This one is fine. This one is fine. Now, there are different ways to do these correctly. I've just chosen one. But, for example, if I start at this carbon, go here, here, and here, then I'm stuck. I can't backtrack. That's 4. 1, 2, 3, 4. But there are different ways I could get 4. I could get 4 this way. That's still 4. I could start at the other end, and I could go this way. 1, 2, 3, 4. It's still 4. So I could start down here and go down this way. 1, 2, 3, 4. But no matter which way I go, I get 4. So you see the one where I've made a mistake. It's this one, right? I have circled a branch. So that's wrong. So let's erase that. And let's start here. When I get to this branch, I can pick any direction to go that I want, but I can only go one of the 3 ways. So if I go up to the top, then I can't also get that one over at the left side. 1, 2, 3, 4. So in each case, there are only 4 in the longest continuous chain. And so what number 8 tells me is that butane is the base name for each alkane in the table. So pause the video and fill in the definition of base name. Pause now. So did you say this? The base name of a branched alkane is the longest continuous carbon chain in the branched alkane? That's the most obvious answer, probably because if you look at the information, it talks about carbons connected in a continuous manner, but even better than that, a circle has been drawn around the longest continuous carbon chain. Sure enough, that's what we've done. Now I could have just defined that for you at the beginning, but the way that this activity works, like most of the activities, is you get a chance to do it yourself before we put the words on it. Now when I say the longest continuous carbon chain, hopefully it means something to you more than just a bunch of words. It's something that you can actually apply to some molecules. Number 9. Draw a box around each branch that extends outside the circles. For example, the first molecule looks like this. So that would be this one. It would look like that. Put a box around it. How many carbons are in each of your boxes? Well, we can't do that until we've drawn the boxes. So pause the video and go up here and draw the boxes. Pause now. Okay, so if I count the total number of boxes, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Even if you circled different base chains, for each of the molecules you should have the same number of boxes. So just for example, on this one, when I circled the base at the bottom and I have 3 boxes, if I had circled a completely different base chain, so let's say I pick this one, which still has 4 in it, when I make the boxes, I still have 3 boxes. So whichever one you have, it will be fine. It'll come out exactly the same. So how many carbons are in each of your boxes and how many hydrogens are connected to the carbon in each box? Pause the video and fill in those blanks. Okay, compare your answers to mine. Number 10. What is the name of the alkyl substituent in each box? The one that has 1 carbon and 3 hydrogens. Look back at table 1. Pause now. So that's called methyl. Right? If it had 2 carbons, it would be ethyl, 3 would be propyl, etc. Number 11. What is indicated by the prefixes di, tri, and tetra on some of the names in table 3? So, take a minute, pause the video, study these in the table and their names, and then write what is indicated by the prefixes di, tri, and tetra. Pause now. Oh, you know what? And as I did that, I realized I forgot to box this one, because that's also a methyl substituent. So there are actually 16 boxes there, 16 methyl substituents. And you know, that word substituent doesn't roll off the tongue so nicely, and so a lot of times we just say group, so methyl group, much easier to say. There's another word that organic chemists use that I hate, moiety. I don't even like how that word sounds. You'll never hear me say it. Well, you just did. You'll not normally hear me say that word. So methyl group, methyl substituent. So the prefixes indicate the number of methyl substituents. Di would be 2, tri would be 3, tetra would be 4. You see it, right? 4 is tetra, 2 is di, and this one only has 1, so it doesn't have a prefix. So I guess we don't need mono. Okay, so number 12. The first 3 structures in the left column are all named 2-methyl-butane. What is indicated by the number 2 in these names? So take a look at those and see if you can figure it out and write a sentence. Pause now. All right, so hopefully you see this. My sentence says the 2 indicates that the methyl group is attached to the second carbon of butane. So do you see it? If I start from this end, then that methyl group is attached to this one, which is the second carbon. Carbon 1, 2, 3, and 4. If I do on this one, and I say it's attached to the third one, fourth, but if I count from the other end, 1, 2, 3, 4, the methyl is attached to number 2. And then on this one, it's also 2, so I must, on this case, again, be needing to count from this end, 1, 2 with the methyl, 3 and 4. You see it? Good. All right, number 13. Explain why 3 numbers are needed to name the molecule 2, 2, 3 trimethylbutane. 2,2,3 trimethylbutane. So that would be this guy. So write a sentence that says, why do you need 3 numbers for that molecule? Pause now. So here's my sentence. Hopefully you were able to figure this out. 3 numbers are needed to describe the position of 3 methyl groups. So there's 3 methyl groups, 1, 2, 3, and so you need 3 numbers. And the numbers are 2, 2, and 3. So if I start right here, this is number 1, number 2, and number 3, then there's a methyl on 2, there's another methyl on 2, see how they're both connected to number 2, and the final methyl is on 3, and nothing on 4. Okay? So let's sum that up. Oh wait, number 14. So you can look right at this name here to answer this question. What punctuation mark is used in names between 2 numbers? You see it? It's a comma. And what punctuation mark is used in names to join a number and a letter? Okay, that's not a dash. I love punctuation. That's called a hyphen. When we talk about that in web addresses, people will say dash when they mean hyphen. My email address is Garut-M, not Garut-M. A dash is a long thing. A hyphen is a short thing. And there's actually 2 kinds of dashes. I can talk all day about punctuation, but I know you're bored, so let's move on with the information. This is going to sum up the rules that we've sort of just developed. So this sums up the rules for how do you name branched alkanes that have multiple substituents. I'm not going to read those out loud to you. You can pause the video and read them to yourself. Then you can look at 2 examples of some other branches, and these have not just methyl groups, but as you see, they have different kinds of substituents. Okay? Pause the video, read this, read question 16, answer question 16, and when you have that answered, restart the video. Pause now. All right, so 3-methylbutane is incorrect because it violates rule number 2, which says you should start numbering the base at the end closest to the branch. And so if you start at the wrong end, you get 3 where the branch occurs. But if you start closest to the branch, then you get 2-methylbutane, which is the correct name. Okay? Number 17. The 5-carbon chain circled in the structure below left, this box on the left, is not a correct one. In the second drawing, circle a correct 5-carbon base chain and refer to rule number 1, which says if 2 chains have the same length but different branching, choose the one with more branches. So pause the video and find a better base chain for number 17. Pause now. Here's one correct answer. Notice that in this one that's incorrect, there are only 2 branches. I should use squares. There are only 2 branches. In the one that I've drawn, there are 3 branches. So if you have circled a chain that has 3 branches, like mine does, even if it's different, then you should just leave it the way that it is because it's perfectly fine. And now you can use the rules in order to give the correct name for the molecule, but make sure that you're using the box where you've circled the correct base chain. Pause now. All right, so I'm going to work through this one step by step. So we've already circled the correct base chain. That's rule number 1. Rule number 2, number them starting at the end closest to the branch. So if I start at this end, this is 1, 2, there's a branch. 1, 2, there's a branch. That's the same. So let me just verify. There's a branch at number 2. If I start from this end, 1, 2, 3, there's another branch. 1, 2, 3, there's another branch. That's the same. Okay, it doesn't make any difference which end I number it from. I'm going to go ahead and write the numbers there So let me erase my circle just so I can fit these numbers in. 1, 2, 3, 4, 5. If you had a different circle, your numbers will be different, but that's fine. Go ahead and do yours your way. Rule 3, name each different substituent in alphabetical order. So let's kind of take inventory of what we've learned so far. We have a 5-carbon base chain. So I know that the name of this is going to be the 5-carbon chain, and the 5-carbon chain is pentane. I know that from table 1. Penta means 5. And now I'm going to look at the substituents that I have in the boxes. That's rule number 3. Name each different substituent in alphabetical order. So in this box is a 2-carbon substituent. That's ethyl. In each of these boxes is a 1-carbon substituent. That's a methyl. That's a methyl. If there are 2 equivalent substituents, add the prefixes di, tri, or tetra, etc. Well, I have that. There's 2 methyls. So that needs to be, so if I put those together, those are going to be dimethyl. And now, finally, give each substituent a number that corresponds to the number of the carbon of the base chain to which it is connected. So I did already number my carbons. So this is 2, right? This one is 4, and this one is 3. And then I have to put them in alphabetical order. Now the thing about alphabetical order, which you may not have known because it doesn't say so in the rules, but these prefixes don't count when you alphabetize. So when I put them together, I have ethyl and I have dimethyl, but I put the ethyl first because ethyl comes before methyl. I don't count the di when I'm doing the alphabetizing. So I need to put 3 ethyl, and in between the 3 and the ethyl I put a hyphen, and then 2, 4 dimethyl, 3 ethyl, 2, 4 dimethyl, and then there really should not be any space because the rule doesn't say to put any space in, and so here's the name. 3 hyphen ethyl hyphen 2, 4 hyphen dimethyl pentane. When I read that out loud, I'm not going to read the punctuation, but when I write it, I have to put it in. When you try to do this on the sapling homework, you have to put in the punctuation correctly, put in the spacing correctly. But I'll say this out loud as 3 ethyl 2, 4 dimethyl pentane. No space. And again, when you alphabetize, you do not count the prefixes di, tri, tetra for the naming. Okay, now it just gets a little bit more complicated. Sometimes the substituents themselves are branched. Also, you can have other substituents besides alkanes. So this table is to learn 2 different things. If you have if you have halogens called the halides, then F is fluoro, Cl is chloro, Br is bromo, I is iodo. We're just going to memorize those. And then if the substituents themselves are branched, this can get really complicated. We're only going to learn the branching up to 4 carbons. So a 3-carbon branch is called isopropyl. And there are 3 different ways to do a 4-carbon branch that we're going to learn. And when you alphabetize these, and I'm sorry I didn't make up the rules, I'm just explaining what the rules are, we do count the iso when we alphabetized. So isopropyl would come before dimethyl, because you count the I, which comes before M for methyl. I'm sorry, again, I didn't make the rules. I just tell you how they are. All right, so do you need to commit these to memory? Yes, you do. And we're going to practice those in the exercises here, so you'll get the idea. Some of these you've probably actually heard of before. Have you heard of isopropyl alcohol, which you can buy at Target for 79 cents? It's called rubbing alcohol. I think you probably have heard of that. So some of these you probably have heard of. Number 19, let's try it. Draw the molecule implied by the name 2-methyl-3-propyl pentane. So let's just do that part first. So pause the video and draw that molecule that name implies. Pause now. All right, so I'll walk you through this one too. When we draw molecules, it's really easiest to start at the end and work backwards towards the beginning. That's the same way that as we named them, right? We started with the pentane, which is the base name, and then we put the substituents on in front of that. So I'm going to use the stick structures because it's the easiest for me. If I want pentane, then this is pentane. 1, 2, 3, 4, 5 carbons. Then I need a methyl on number 2. So that's number 2. Put a methyl. And on carbon number 3, I need a propyl. So here's carbon number 3, and I need propyl. 1, 2, 3. There's a stick structure for the molecule that's implied by this name. Now if I look at that structure, I'll find out that the name is actually incorrect. So go back to the set of rules and apply them properly, and then name this molecule. Pause now. Okay, so did you see that pentane is not the longest chain? That if I trace the longest chain possible without backtracking, I can actually get 6. Here's one that I did. 1, 2, 3, 4, 5, 6. There are different ways you could circle 6. If you circled this 6, however, like this, that's 6, but that would not be the correct 6. Why not? Because that has only one branch hanging off the side of it. And so, and so the circle that I have here has 2 branches, so that's acceptable. So you have to make sure you follow the rules. So now when I do that, I'm going to number it mentally, counting from this end because that's closest to the first branch. So this is a methyl on number 2. This is an ethyl on number 3. So I have 3 ethyl, 2 methyl, because E comes before M and you alphabetize. And then I don't put a space. And then this is 6 carbons in my base, so hexane. All right, you see how that works? These rules that you're learning to name alkanes, and actually one other thing, when you have halogens on them, they're called haloalkanes. Hence the title alkyl halides. That's another name for haloalkanes. So in this activity, we've now learned how to name alkanes, cycloalkanes, and alkyl halides, also known as haloalkanes. And these substituent names are things you should memorize. Now I realize that's a lot, so I'm going to be honest with you and tell you the ones that come up more commonly are the isopropyl and the tertiary butyl, which we sometimes just say tert-butyl. The isobutyl, the sec-butyl or secondary butyl don't come up nearly as commonly, so if you're having trouble memorizing all of them, get those first. So then we have exercises where you practice this. And again, the way that I suggest doing this, and I think it's extremely important this time, is that you do them one at a time. So here's a table where you have the name, the complete Lewis structure, the condensed formula, the stick structure. So you're given the name and you fill in the other three. So try to fill in those three, then look at the answer. For the second one, you're given the condensed formula, so try to fill in the other three, look at the answer. And you're going to get some practice with those. You'll have, if you want more practice, you can look in your Frost textbook. And of course, you'll get plenty of practice on the sapling homework for this section. This completes the screencast for Chem Activity 33. Cheers!